So welcome back. This is machine learning, which is COL 774, and today is April 22, 2020. So last class, remember, we were looking at expectation maximization algorithm or the EM algorithm, and the sort of intuition that we discussed was that we had this LL theta, which was a complicated looking expression, and we wanted to optimize this, right? We wanted to get arg max over theta of LL theta, which was nothing but P of xi parameterized by theta, and log of this, and then sum over all examples. Right, so we wanted to do sort of arg max of this LL theta, which was essentially uh, this expression. And the way we did this was that we constructed a lower bound to this function, right, which was LL prime theta at a given theta t, and instead sort of optimize this lower bound, right, which was supposed to be tractable, right? And right, this sort of gave us two steps. E step, which was to construct the lower bound, and then M step, which was to optimize the lower bound, right? And then we sort of repeated this process again and again, right, of constructing a better lower bound and then optimizing that better lower bound, and we sort of showed right, that this process actually converges to the local optima of this LL theta function, right? um, or at least give a very broad indication of why it should converge to the local optima of the log likelihood function, right? So now let me describe the entire thing more in a algorithmic schematic. Okay, let's proceed further with the actual EM algorithm, expectation maximization. The input is a set of examples xi I equal to 1 to m, and it proceeds as follows: t equal to 0, right? This is sort of your initial iteration. Theta t is some initial set of parameters in it, and then you repeat the following steps, which is a combination of the E step and the M step, right? So let me write the E step first, which is nothing but estimating these distributions Qi, Zi, given the current set of parameters, which is theta t, and this estimation can be done by maximizing the following expression with respect to Qi, Zi, which is Qi, Zi log of P of xi, zi, theta t, right, which is sort of uh, the right lower bound, right? So this entire expression, right, if you will, is essentially the expression for the lower bound at theta t, right? So this is LL prime evaluated at theta t, right? And this is the contribution of example I, right? So this is contribution of xi, right, to LL prime theta t, right? And what we really want to do is that because we are constructing this lower bound at theta t, right, we wanted to find that distribution Qi such that this lower bound touches the original function LL theta at theta t, right? And since the lower bound is touching the sort of the original function, right, it has to be sort of uh, the quote unquote the best lower bound at theta t, which is obtained by maximizing with respect to this distribution QIZI, right? In other words, QIZI is that distribution which will sort of maximize this lower bound at the given point theta t, and which is exactly why we have this argmax, right? And we know that right, we have seen that earlier. This entire expression will result in, you know, this expression p of zi given xi uh, parameterized by theta t, right? So once again, right, this is the expression that we wrote earlier, but equivalently this can be written as you know, argmax of over qi of this expression qi log pxi theta t over qi which essentially is sort of the expression for the lower bound, the contribution of example xi to the lower bound, and we are sort of maximizing this lower bound at theta t to get the expression for QIZI. Okay, and the next step is the M step, right, which says that, you know, once you have constructed this lower bound, right, once you have obtained this QIZI, right, we would like to now see this lower bound as a function of the theta parameters, right, and then right, estimate our new theta parameters, which is theta t plus 1, um, right, and these theta t plus 1 parameters are nothing but argmax over theta of uh, this lower bound seen as a function of theta, right, which was constructed in the previous step, right? So now we know what QIZI are, right, and we want to uh, maximize this lower bound as seen as a function of theta, uh, right, and then maximize this with respect to theta parameters, right, and this is our M step. Right? And maximizing this with respect to theta will give us a new theta t plus 1, right, which will, you know, now lead us to constructing a new lower bound at theta t plus 1, which is the E step, and then again sort of the M step at this newly constructed lower bound, and this process sort of repeats itself, right, until convergence, right, and right, t goes to t plus 1, right, and we sort of repeat this, right, so repeat this process until convergence, right? So this is a sort of our entire EM algorithm. One thing I want to remark here, which we will sort of look at in the next slide, is that note that in both the E step and M step, right, this is sort of a very uniform treatment, because now we are maximizing the same expression, which is sort of this QIZI log PXIZI theta t over QIZI, which is nothing but contribution of the ith example uh, to the LL prime theta t, but in one case we are optimizing with respect to QIZI, and in the other case we are optimizing with respect to theta. Just one more sort of correction here, that in M step this is all over all I equal to, right, sum over all possible examples, right, and in the E step, right, this is for all. Okay, I think let's proceed to the next slide. Just a few more remarks here, right, on sort of the EM algorithm, right, which is the expectation maximization algorithm, right, on the previous slide. The way we have described this on the previous slide, it is interesting to note that the entire sort of EM algorithm, right, which is sort of maximizing, trying to find the local maxima of this LL theta, which is, remember, nothing but P of P of xi parameterized by theta log of this, and then sum over all examples, right, so this is sort of our log likelihood, right, and then we are trying to maximize this with respect to theta, but alternately it can be seen, right, so this is argmax over theta, um, but right, the sort of the EM algorithm can be seen as doing this, you know, via two-step process, which is argmax of uh, the expression which was essentially the expression for the lower bound, right, over qi zi, right, and argmax of this expression with respect to two sets of parameters, which is qi zi and theta, right? So note that what have we done here? We have said that instead of optimizing the original log likelihood function, we can instead optimize this changed objective, right? This is our sort of new objective, which is qi zi log pxi zi parameterized by theta over qi zi, and then optimize this with respect to two sets of parameters qi zi, right? And this is there should be some here, right? Some overall examples, right? And this is for all I, right? And this is exactly what we have done on the previous slide, right? That you sort of maximize with respect to these two sets of parameters, one at a time, right? So you optimize this with respect to qi zi, right, for all I given the theta, and once you know the theta, then you sort of again optimize this with respect to um, right right qi zi, and then once you know the qi zi, then you optimize with respect to theta, right? So you go back and forth, right? And this essentially is an algorithm which is called dual coordinate descent, right? And I will talk about it in a minute, right? But once again, what are we doing here is that we are fixing a set of parameters, right, which is, let's say, qi zi, right, and then optimizing with respect to theta completely, right? Remember, right, the lower bound is completely optimized, right, right, and that sort of descending, right, it should be descent, right? So it's sort of ascent along theta, and once we have optimized theta, then we go to the other set of parameters, which is qi zi, and then ascend along those parameters, and repeat this process, right? And as I said, I will say a little bit more about it in the next slide, but I want to make a couple of remarks here, uh, and maybe let me make them on the next slide. Okay, so the first remark that I want to make here is about Hardium, right? And in Hardium, what typically happens is that, right? Let me write the expression here, right? We had argmax over qi zi for all I equal to 1 to m theta of qi zi summation over I equal to 1 to m log of p of xi zi theta over qi zi, right? And in Hardium, right, in the step when estimating qi zi, right, instead of taking the distribution, sort of the entire distribution, right, we rather say that we are going to fill in with one specific value of zi, which is sort of your value which maximizes this distribution, right? So instead of using the uh, the entire distribution, right, right, obtained from the e step, right, you rather fill in with respect to zi, which is the maximum value of qi zi, right? So this is sort of Hardium, and this is nothing but what we do in k-means, right? That we sort of select the single assignment, single cluster assignment, and go to the next step, right? So k-means is a special case of Hardium with appropriate sort of covariance matrices, which is a sort of identity in GMM, right? And right, and this could be done in general, not just in case of k-means, that instead of using the entire distribution qi zi, um, right, you use the value of zi which maximizes qi zi in the next m step, right? There is also something called generalized EM, right, or generalized expectation maximization, where in the M step, right, when you do argmax over theta um, of LL prime theta, right? I'm just writing this in the form of LL prime theta, right? Then instead of doing the full argmax, right, you don't optimize it fully, but only optimize it, um, right? Optimize only for a few steps, right? And that is still okay because you are still sort of improving the lower bound, right? So instead of optimizing your lower bound completely in the M step, yeah, right, you optimize it for a few steps, and which can be useful in cases where your LL prime theta is also not easily computed in closed form, right? So you optimize it for a few steps and then you get a sort of a better theta t, uh, which may not be the optimal for lower bound, but it is still a better estimate than the previous theta t. And then you construct the new lower bound at this new theta t plus 1, right? And there is a paper, right, I guess a series of papers, right, on generalized EM that I can point to offline. Okay. And finally, I want to talk about dual coordinate descent in the next slide, right, that I had mentioned earlier in the context of the EM algorithm. Uh, Now, on this slide, let me describe something which is more general, which is applicable, beyond just EM, which is called coordinate descent. Right. And here is the idea. Let's say you have a function which is function of two parameters f theta 1 and theta 2, right? And let me sort of draw this and which you want to maximize, let's say, with respect to these theta 1 and theta 2 parameters, and assume that theta 1 and theta 2 are scalars, right? So this is, let's say, theta 2 and this is theta 1. um, right, and let us draw the contours of this function in this space theta 1 and theta 2, right? And this is our goal, to sort of reach this point which is the maximum of this function, right? Recall some of the lectures that we have done right in the beginning of this course, right? And how did we sort of do this? We said, okay, you start with some, let's say theta 0, right, which lies here somewhere, and then you follow gradient descent, and gradient descent will sort of follow a path, right, which will be sort of normal, right, to right, these contours at every point, and then essentially it will sort of get very close to the optimal, and optimal, right, with a sufficiently small learning rate, right? So this was, let's say, gradient descent. Then we also looked at Newton's method, right, which used additional curvature information, right, to sort of maybe move faster, right, to this point of optima, right? And we saw that in case of quadratic functions, right, in fact, it could optimize the function in just one step, right? So this was Newton's method. Okay, but in coordinate descent, we take a slightly different approach, which says that instead of either doing gradient descent or something like Newton's method, right, which is a second order method, we are going to optimize this function, using coordinate each coordinate in turn, right? So what you will do is that you will start with your theta 0, right, which is essentially your theta 1 0 and theta 2 0, right? So these are sort of two coordinates, right, of theta, and then fixing one of them. Let's say, in the first step, you will fix theta 1, and then you will optimize with respect to, let me use a different color, right, red color here, right? So you will optimize with respect to, let's say, theta 2. Right, so you will descend in the direction of theta 2 right? You will right, and that means searching the best point along this line, right? And it is not very difficult to see this will be somewhere where this curve, right, this vertical line is tangent to the contours of the function, right? And once that has been done, right, once you have optimized this with respect to uh, theta 2, then you optimize this with respect to theta 1, and which will be searching the optimal of this function along this horizontal line, right, which is searching for theta 1 while fixing theta 2, right? And then once again, right, you will search fixing theta 1, you'll search along theta 2, and so on and so forth, right? And then maybe, right, you will reach the optima in few, right? So this is called coordinate descent, because you are sort of descending along um, each coordinate at a time, right? And I've sort of described this in terms of descent, which is sort of actually for minimizing, but you can do for maximization also. This is just coordinate descent, or coordinate descent, if you will, right? And that this right, I've described this more sort of informally, but I hope, right, the details are clear. And this is a fairly popular way of optimizing a function. And what is interesting is that this whole sort of coordinate descent or ascent is guaranteed also to converge to the same point as sort of what your gradient descent does, which is sort of the local optima of the function, right? And note that maybe it will discover a different local optima, right? If there are multiple local optimas, maybe it will discover a different local optima, but this algorithm is guaranteed also to converge to one of the local optimas of the function. And where it is useful in cases where optimizing the sort of taking the gradient of the entire function may be difficult, but it is easy to optimize with respect to these coordinates, one at a time, right? And and um, right, so and a generalization of this is called block coordinate descent, uh, right, where we optimize with respect to blocks of variables rather than optimizing with respect to a single variable, right? So we divide the variables into sets of blocks, and then we sort of optimize over each block in turn, and this is called block coordinate descent. And in particular, the EM algorithm that we have just described, right, argmax over qi zi I equal to 1 to m theta of qi zi log p xi zi theta over qi zi is an instance of block coordinate descent, where the blocks of variables are qi zi, right, for all I, right? So this is one block of variables, so you optimize with respect to that, right, completely. And then once you optimize with respect to qi zi, right, you go to theta, which is again a set of variables optimized with respect to theta, and you go back and forth, right? So this is called block coordinate descent. I might have used dual coordinate descent on the previous slide, but it's actually block, right? So dual um, coordinate descent is something slightly different, which is you are optimizing with respect to two variables at a time, but in general this is a block, for example, in this case, of variables which could be more than two in general, right? And finally, this block coordinate descent is also used with SM algorithm, which is sequential minimal optimization for SVMs, right, which you can read from the notes, right? Right, that's in the SVM notes. If you're interested, you can read those notes by Andrew and G. But what you should definitely read, which is part of syllabus, is section 9.1, right, in the notes by Andrew NG on SVM. right? So this please make sure to read this section 9.1 on SVMs, which is describing this coordinate descent, right? So this section is not specifically, or rather, this section describes coordinate descent in general, right? Coordinate ascent or descent, right? So and this will be part of the syllabus, right? So please make sure to read section 9.1 on SVMs from the Andrew NG notes posted on the course website, and that describes the coordinate descent algorithm. Right? I do not really expect you to know the SMO algorithm, which is the next section, right after 9.1, but 9.1 describes the coordinate descent algorithm in general, and that is what you should really read. And this is essentially what I've described here also in this slide. Okay. Before we go to the next topic, which is PCA, I just want to make uh, just a couple of remarks here. So the first one is that in the previous slide we have used this expression, uh, which is we are trying to do argmax over right qi zi, right, I equal to 1 to m, right, and then theta of this expression, which is qi zi log of p of xi zi parameterized by theta over qi zi, right, and I think I might have forgotten the sum here, right? So this is important that there is a sum here, I equal to 1 to m. So this is sort of over all the examples, right? So we do sort of block coordinate descent on this expression. Second thing I want to mention is that we refer to this algorithm as block coordinate descent, and not really as I might have mentioned, dual coordinate descent, because dual is when it's a block of two variables, right? But we are doing it in general, so this is block coordinate descent. So please correct that, right? Only in the context of SVM it is dual coordinate descent, but in general this is block coordinate descent that we are doing, right? And these are two things I wanted to keep you in mind, and then we'll start with now next topic, which is our principal component analysis. Okay, okay. So let's get started with the new topic, which is principal component analysis, right, or PCA, and this is a technique for dimensionality reduction, right? And let me give you some motivation with the help of this figure. Right? Let's say, right, you have bunch of data points sitting here in 2D, right, and this is our set of data xi equal to 1 to m, and let's say it's just two-dimensional data x1 in denoted by these features x1 and x2, right, and these could be for example attributes such as your GRE score and SAT score, right? So GRE is the score of the exam that you typically take for graduate studies, for example in US, and SAT is typically the score that they require for admission into colleges, right? And what this data is saying is that although you have two different dimensions, right, x1 and x2 here, GRE and SAT, right, there is high correlation between these sort of scores, right, and this correlation is essentially captured by this vector view, right, that we would be interested in finding, right, in case of PCA, right? So what we are saying is that, right, although your data sort of sits here in two dimension, uh, right, in the raw form, but essentially, right, the pattern in the data is more or less one dimensional, which is given by this vector u, right? And this is just a two-dimensional example, but in general, your data could be sitting in a very high dimensional space. For example, it could be sort of your set of images, right? Each of these xi's could be your set of images, where each xi might come from a space, uh, which is let's say r to the 1000 maybe, right? Or let's say 10,000, right? Which is sort of your 100 cross 100 images, right? This is 10,000, right? So this is 100 by 100 images, right? And then the question is, right, given such a high dimensional space, right, can we sort of project this data onto a lower sort of set of dimensions, right? In this case this was one dimension, but in general this could be u1 to uk, right? So these are sort of your k uh, dimensions on which you project, right? And each of these ul, right, in the original space still belong to Rn, right, where n was this 10,000, right? But this k typically is much smaller than n, right? Right, so again coming back to this example here, right? So each um, data point here, let's say this was let me use the red pen here, let's say this is xi, right? And right, this xi could now be represented in terms of this single vector u in this case, right? And how the way to represent this would be, we'll sort of project this data point onto this line u, right? There could be, for example, another point here, which could be, let's say x, this is xi, right? So maybe let's say x I prime, right? And this data will also be projected on this line, right? And what will happen is that we will get for each of these data points we will get these projections z1, z2, right, and up to z or zm, right? So these are right, let me sort of not write here, right? But I think, right, so this projection is sort of your point zi, and this is your zi prime, right? And what we are really interested in is finding this u, so that most of the information, most most of the information in data is still captured after the projection, right? So instead of right looking at original sort of xi equal to 1 to m, right? Instead, if we look at projections which are zi I equal to 1 to m, right, which are projections along these u1 to uk, right? Or in this case just this single dimensional u, then we would of course in general there'll be some loss of information as you project it, right, unless the data is perfectly correlated, right, like right, for example in this case, right, unless the data sits completely on the u line, right, there'll be some loss of information as you project it, but you would like to really sort of minimize this loss and still project onto a much lower dimensional space where for a given k, where k is much less than n, right? And in fact, as you will see that this k could sort of also be sort of dynamically decided, right, for a specific sort of application, right? Right, so this is sort of the intuition, and let me sort of continue this in the next slide. So continuing from the previous slide, right, let me sort of draw those points again, right? um, right, so these are your data points, right? Let those which lie in 2D space, right? This is your x1 and this is your x2, right? And this is your line u, right? And you would like to project on the points, right, each of these, let's say xi's, right? So maybe there is a point here xi onto this line, right, which will actually be a vertical projection here, right, which is zi, right, and so on and so forth for every point on this, right? And as you can see, right, this u is a good projection line, right? Because for example, right, if you were to project this data onto a different line, right, maybe your if your u prime was something like this, then what will happen is all your data will essentially project between these two sort of points, right? So if you decided a different direction u prime, right, which is sort of perpendicular to this u, then you can see that this is not a good direction for projection, because all your data will be squished between these two uh, markers, and which is right. So this leads to a large amount of loss of information in the data, right? So what we are looking for is, in some sense, best set of u1 to uk, right? And for now, let's say k is given to us, right, these sort of dimensions, right, right, which sort of minimize this loss of information in the data as data is projected, right? That's sort of the intuitive argument, right? And now the question is, right, why project the data, right? Why project it, right? So as it turns out, like in the above case, right, so the first one is right, there is a notion of discovering hidden pattern in the data, right? So this projection would essentially enable you to sort of discover some hidden pattern in the data, right? For example, in this case, right, the fact that the scores are highly correlated, right, and in fact, right, you could almost right, with complete information, right, you could represent them instead using a single dimension in this case. But what is sort of more interesting from a utility point of view is that projecting uh, onto a lower dimensional space would make things much more tractable, right? So once you project your data onto a sort of a lower dimensional space, right, the sort of future competition will become much more tractable, right? Because remember that typically k is much less than n, right? And you could sort of now once you project it, right, you could do sort of your entire computation in terms of these new subspace, right, or new space in terms of u1 to uk, uh, right? In fact, the data will be expressed as coefficients of this u1 to uk, right? And this could be computationally much more efficient to deal with this data in the projected space. And third, I think, which is also very important, is that often this will also help us reduce noise in the data, right? So the assumption is that, right, much of this variance, right, um, right, which is uh, sort of not represented by this line, also could be due to noise in the data, right? So what we are saying is that the underlying assumption is that, right, there is noise in the data, and if you remove that noise, right, the data might almost perfectly lie in this lower dimensional subspace, right? And if you project onto that lower dimensional subspace, then you would essentially, right, there'll be some loss of information, but most of that information which is lost is actually due to noise, and this reduction in noise will also lead to avoidance of overfitting, right? When you learn, or when you do learning with projected data, right? So this is the third sort of advantage of this, right? Right. So once again, right, we would like to discover hidden patterns in the data, and then right, projecting onto this lower dimensional subspace can make things much more sort of computationally efficient. And third is that it might have an additional advantage, that it will actually reduce sort of noise, leading to avoidance of overfitting in the data. And before we go any further, I just want to sort of repeat again to avoid any confusion, that right, in the diagram here, right, this u dimension is essentially, right, is what you are really interested in projecting the data on this, which is sort of this blue line, right, which preserves right most of the the variance, as we will see in the data, which leads to minimal loss of information, right? This is sort of the dimension, right, shown here, right, by u, and this u prime is the dimension which actually leads to loss of information, a large amount of loss of information in the data, right, which is perpendicular to this u dimension, and u prime is not a good dimension to project the data on, right? And what we are looking for in PCA is to find this sort of best u which captures most of the information in the data. Okay, and before we proceed any further, right, I just want to say one more thing about this diagram that we saw just earlier, that we're looking for this u dimension, right, which preserves most of the information, and the way we will sort of quantify the loss of information is will be in this terms of this variance of the entire data, right? So maybe right, with slight abuse of notation, right, I'm just writing this as sort of total variance in the data, which is sort of variance of this entire sort of data. It will be given by variance along each of the dimensions. So xi minus xij minus mu j, where mu j is the mean along the jth dimension, right, and the square of it, and I equal to 1 to m, right, and 1 by m, right. This is the variance along dimension j, right, and then, right, this is done over j equal to 1 to n, right. So this is sort of your entire variance in the data, right, that is the variance of in the original data, and as we project the data onto, let's say, zi's, I equal to 1 to m, right, and these are projections on the U space, which is U1 to UK, right? Right, we would like to really sort of right, minimize the loss in the variance over this, right? So in particular, we will define variance in the projected space, which will be sort of variance over these ZIs, right, which have been projected onto this U1 to UK, right? So we'll compute the variance not along the original dimensions, but along these projected dimensions, right, and I'll give you the formula for that, but the whole idea is that this variance should be as close to the variance in the original data, right, right, so that the loss in the information is sort of maximized, right. So note that here the variance is sort of capturing the total amount of variance in the data, and this is also equivalent to the amount of information in the data. Okay, so let me now formally describe the problem setting, right. So the problem setting is as follows, right, that there are these bunch of data points xi I equal to 1 to m, where each xi, right, belongs to Rn, right, and we want to find, right, project this data onto these dimensions. Let's say, um, let me make the notation clear, right. This is u1 up to uk, right, right. So our goal is to find this u1 to uk, right, which is sort of the projected, which represent the projected subspace, right, where each ul uh, is right, each ul belongs to the original, right. Each ul can be represented in the form of the original n-dimensional space, right. So each ul belongs to Rn, and right, you want to find this u1 to uk such that, right, each xi now can be approximately represented as zi, right, where zi are these projections, right, of these xi points onto this u1 to uk dimensions, and therefore zi can be written in terms of these components zi1 to zi k, right, where zi k is nothing but the projection of this xi point, right, xi point on the ul dimension, right, or this should be l, right. So that il is nothing but the coefficient of the projection of xi onto the dimension ul, right, and And note that each of these UL are unit vectors, which means that norm of this ULs is 1, right, which is also equivalent to writing as in the vector form as UL transpose UL is equal to 1, right? So we are interested in finding this U1 to UK, right, such that when we project the data onto these xi's onto this u1 to uk, we get this zi, right, for each point, which is zi1 to zik, where each coefficient zi l is defined as sort of xi transpose ul, which is nothing but the projection of the point xi onto the vector ul, right, and right, this zil is sort of the magnitude of that projection, and the entire zi is represented by k such projection components, right, and as we will see, right, we want to find such u1 to uk, right, which sort of minimize the variance in these projections, which is I1 to M, right, in the new U1 to UK space. Before we proceed further, right, there is an important step that we will perform, right, which is normalization of the data. Right, so in particular, right, given these points, right, data points xi equal to 1 to m, right, will transform them so that right, the resulting data has zero mean and unit variance. Right, and reason for transformation is very similar to what we have done in some of the previous assignments, right. This zero mean um, essentially right, will help us get rid of the bias term, right, which makes some of the computations simpler, as we will see, and but I think more important is this unit variance transformation, and this is important, right. I won't go again in the much detail of why we do this, but remember that we had discussed this, that um, this is important to take care of data, right, in dimensions where each dimension may come from different metrics, right. For example, if your one of your components is weight, right, which may be measured in kilograms or milligrams, other component is let's say height, which may be measured in meters or centimeters, then sort of the relative variance, right, that we capture along each of these dimensions will depend a lot on the units used for respective dimension, right, and we want to just normalize the data to unit variance in each of the dimensions to sort of have this uniformity of scale in each dimension, right, and right, and once again, right, refer to some of the notes earlier, right, about know why we do this. But what is the transformation? The transformation is simply that each of xij now goes to xij minus mu j over sigma j, right, right. So the denominator makes it zero mean, and dividing by sigma j makes it unit variance, right, where mu j is simply the mean of the jth component, right, and this is for all j, and this is for also for all, right, and the resulting data now that we get will have resulting data, right, that we get has is zero mean, right, in each of the dimensions, which will mean that after this transformation xij equal to 1 to j sorry 1 m 1 by m is 0, right, and the variance, right, which is sort of in dimension um, j, will be simply xij, mean is already 0, square of that I equal to 1 to m, uh, 1 by m is equal to 1, right. So this is sort of the variance, and mean after transformation, right? So this entire thing is after you transform the data, right? So this is an important sort of precursor to applying PCA in general, right? Um, there is some kind of data where you may not want to sort of reduce the variance to unit variance, and these are the cases where right each of the dimensions come from the same metric, but maybe I'll talk about that later, towards the end of PCA when we talk about application of PCA for different problems. Okay, so now before we go any further, there is one more remark that I want to make, is that after we have transformed this data to unit variance and zero mean, right? So this is your data, right? Normalized data. Then let's say you want to project it onto these zi's, right? Where zi's, right? Where I equal to 1 to m. Then and the projection dimensions are, let's say, U1 to UK, right? Where each of these ZILs is given by, right? So this ZI can be represented as ZI up to ZI K vector, right? Which is essentially each of these ZILs is nothing but the projection of XIs onto these ULs, right? Then let us just quickly look at, right, what is the mean along these z dimensions, right? Mu zl denotes the mean along of z's, right, along the dimension l, right, where l is from 1 to k, right? This is nothing but I equal to 1 to m, 1 by m, xi transpose ul, right? And then note that this is the left, the one on the left is mu and this is u, right? Anyway, we'll soon see that these mu that else will be zero, and will probably, we can get rid of them, right? Anyway, but let's just do this completely, right? So this is xi transpose ul summation over all examples 1 by m, right? But because ul does not depend on these examples, so what we can do is 1 by m summation I equal to 1 to m xi, and the transpose, sum of transpose is simply transpose of the sum, right? So I can do this, and ul is anyway out because it does not depend on xi's, right? So I've taken ul out, and also I've taken transpose of the entire expression, because right, it sort of commutes with with this sum, right? Right, I can take it out of the sum, right? And therefore, right, this expression is zero, because our data, this is the mean of the original data, and therefore this entire thing is zero, right? So which means that this is for all l, right? So for all you know l, right, in the projected space also the means are zero, right? And this is something that we will sort of use in the next. Okay, so given this, right, what we are interested in is really finding this quantity which is variance of zi's, right? I going from 1 to m in the projected space, right? And let me just first compute the expression for this, and then we will try to right, we will see that we'll actually will be interested in maximizing this expression, because we want to maximize the variance along the projected space, right? But let us look at this expression, right? So this is sort of variance of the data in the projected space, right? And remember, right, this is simply sum over all possible dimensions, right? So variance along each of the dimensions, so going from l equal to 1 to k, right? And then the variance along a particular dimension is 1 by m, right? And remember, the dimensions here are sort of your 1 to k, right? 1 by m, right? Sum over uh, uh, all the examples, right? And then we have essentially your zi's, right, which in terms of written in terms of xi's are nothing but xi transpose ul, right? And because it is variance, this is square of this, and right, note that I have not subtracted the mean because mean is 0, right? Um, because mean is 0 along each of the dimensions, right? So this is our expression for the variance. And expanding it further, right, we will get L equal to 1 to K 1 by M, I equal to 1 to M, right? We will write it slightly differently. We will write it as U L X I U L X I transpose, right? So I'm taking one of these expressions in the square out, and instead of writing it as xi transpose ul, I'm writing it as ul xi transpose, which is the same thing, right? And then xi uh, 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 okay, let me sort of do it again, right? This is not the right way I want to do it, right? The way I want to do it is I want to write it as uh, u l x I transpose, right? Right, I can write the first term as ul xi transpose, which is same as xi transpose ul, and then the second term can be written as xi. I'm sorry, again, I think I am uh, messing it up a little bit, right? Let me try it again. The way I want to write it as I want to write it as ul transpose xi, right? Which is sort of the first term, right? I am writing xi transpose ul as ul transpose xi, which is the same thing. A transpose b is same as b transpose a, uh, and then the second term is written as it is, which is xi transpose ul, right? So convince yourself that xi transpose ul whole square is nothing but ul transpose xi into xi transpose ul, right? And we will see that this expression has an interesting form in the next slide. Right, so let me just take a couple of more minutes, right, just to bring it to a logical sort of conclusion. So this was our variance over z i's, right, I equal to 1 to m, right? This is sort of the total variance in the projected space, and this was nothing but sum over l equal to 1 to k 1 by m, and then we have sum over I equal to 1 to m, right? U L transpose xi transpose ul, right? Which can be written as L equal to 1 to k, and I can take this ul transpose out and take this 1 by m inside. I equal to 1 to m of xi transpose, right? And this does not depend on ul, right? I can keep the l outside, right? And this expression, right, is interesting, because this expression, as we'll sort of see more in the next class, right, and it should not be difficult to see for most of you, is nothing but empirical covariance matrix of the data, right? So given the data, right, which is your xi equal to I equal to 1 to m, right, this is nothing but empirical covariance matrix, because this xi transpose sum over I equal to 1 to m, right? Right, these the components, right, first of all, note that this xi transpose is a matrix, n by n matrix, and the components of it are nothing but computing the covariance between different dimensions, right? So if this matrix is denoted by this sigma, right, then the sigma jk is nothing but the covariance between the jth and the kth features, right? And note that this is actually the covariance, because the mean has been reduced to 0. But in any case, I'll talk about it in the next class.